But looks like it's ready to get going. Yeah. Are you pressing it over? No. Okay. All right, Team 4. We'll turn it over to you. It is.
Hi everyone, this is Cole Child. This is the CDR for Team 4. Our team name is Savior, which is an acronym for Small Autonomous Vehicle with Intelligent Optics for Urban Rescue. Next slide. This is just an overview of what we are going to talk about today. I am going to be covering everything up into aerodynamics. Next slide. Here is an overview of our mission. Our UAS will be equipped with a camera and image recognition software to remotely detect people in distress in a post-hurricane situation, and then transmit back those pictures of the people as well as their GPS location. Approximately, our flight time will be 1 hour. In previous presentations we've given, we've received some feedback that we need to reach out to more stakeholders in regarding to our mission. So recently we talked to a registered search and rescue team in Osseo County, Florida, that works specifically with swiftwater rescue. After talking to them, we determined that we really need to target rural areas. The person we were talking to says that the majority of search and rescue efforts occur in large cities, but small towns that often get hit the hardest are the first to be overlooked. So this person thinks that our UAS would be a perfect solution to these types of communities where helicopters aren't available. So with that in mind, we'll move on to the next slide. Additionally, we received some comments that we need to figure out a way to handle the heat associated with the camera, batteries, servos, Pixie Hawk, and other onboard electronics. After consulting some experts in heat transfer, we did a convection analysis to determine the equation for the heat rate required to cool the payload tray. We determined that the best solution to cool this system would be to cut slots into the fuselage to allow airflow. These slots will be approximately 7 by 1 centimeters, and considering that these slots could potentially weaken the structure, we will reinforce these parts with Kevlar. Next slide. The following picture here is an example of what these fuselage slots might look like. This slide also provides methods we will use for solving the convection analysis to find the heat transfer coefficient for our system. At the moment, we're also currently working on picking a material for a possible heat sink to better allow conduction away from the electronics, and then obtaining a reasonable estimate for the velocity inside the fuselage. Next slide. Okay, so here is a rendering of our updated 3D model for our UAS. The model is created in 3DE and is a total assembly of all the different parts we have made at our respective universities. As you can see, there is a clear dome on the front, which allows for us to take pictures, and then the tray slides in and out, which contains all of our electronics. Next slide. This model represents the shape and dimensions we plan on using for our final UAS. There's also the internal tray that you can't see yet. This tray contains the avionics and other electronics associated with our mission. Some work has been done assigning weights to the different parts and components in the model. However, there's still work to be done regarding getting accurate weights to calculate the CG. Next slide. This slide is a all-encompassing overview of the size and dimensions for our UAS. Other than a slight adjustment to the vertical stabilizer, the information is more or less the same you've seen in the past. Next slide. And here are our production plans going forward into next semester. As you can see, we are intending on manufacturing different parts at different universities and having EDC make our fuselage shell. The fuselage shell is going to be a more difficult part to manufacture considering it's going to require a mold, and we feel like EDC has the capabilities for that. Additionally, we would like them to integrate our polycarbonate nose dome to the fuselage and make that removable so we can get to our tray. Additionally, we'll be doing quite a bit of 3D printing for our mounts, and then doing wet layup with carbon fiber for our wings. Next slide. Here's an example drawing of what we've been doing here with 3DE. This is the internal rib that we will put into our fuselage, and this rib, as you can see, has notches for 2 different trays. I imagine we'll separate components based on their weight so we can fine-tune our balance and CG. We intend on using Velcro on these trays just to make things a little more maneuverable. Next slide. And here is the glider that we've been hard at work doing. This glider has been manufactured here at BYU. It is full scale. As you can see, it's just a 2-liter bottle right now for our fuselage, which has also been a great way to adjust the weight. Currently, it's filled with sand, just to see if we could support that much weight on our boom and our wings. When we did our glide test, we removed that sand. But really, we were trying to mimic actual manufacturing processes. We've 3D printed our mounts, and the vertical and horizontal stabilizer is made from a wet layup foam core. Next slide. Empty weight, our glider came to 3.135 kilograms, and then to mimic our full design weight, we filled it with sand and added some weights to the front to get to our total 6.192 kilograms. That's our expected weight with the controls and camera gimbal system. After making this glider, we believe that that's a reasonable amount. It should be achievable, especially with the aerodynamics that we've taken into account for. Next slide. And here we are testing. Our first test was a short distance, and then we did a much greater distance from a top of a hill. To calculate our glide slope, we took the height of takeoff, and then additionally we determined how far the plane flew. We were really surprised to see that it remained intact, or more or less intact, when it landed, which means we can continue to prototype and reuse our wing and tail and boom. Just to mention, the boom is the boom that we intend on using with our final plane. We purchased this boom from Rockwest Composites. We sized it and determined that this boom should account for our needs going on. Next slide. And here are some simple lessons we learned. The first is that challenges arise when we don't take into account manufacturing processes and materials. We realize that it's very difficult to obtain foam that's greater than 2 inches. If you go to Home Depot or off the shelf, most extruded polystyrene is that pink stuff, which is 2 inches. Consequently, our wing is a little thicker than that, so we ended up having to acquire some expanded polystyrene, which is the white foam. It's a lot lighter and a lot softer, and we encountered challenges with that as well. As we were attempting to do some of this wet layup here at BYU, we realized that it's pretty difficult to get a good surface finish. It requires using a specific type of peel ply, and also having good vacuum. I think we definitely learned what we need to in order to get a better product in the end. Next slide. And here's an example of a bad surface finish. We tried doing a carbon fiber layup on our wing, and for some reason the foam collapsed under the vacuum, possibly because the expanded polystyrene is just a little too soft and we didn't have the right tooling. So consequently, with our glider, we ended up cutting new foam, and that's what you saw previously was our wing without a carbon fiber skin. But for the final glider, we plan on repeating this process, just making a few tweaks. Next slide. All right, so I'll be handing off the rest of this presentation to Tristan from Georgia Tech.
All right, and with that, we move into UAS design analysis. For the main wing, our goals when designing it were to reduce stall speed, increase endurance, and have efficient cruise around 15 meters per second, which is our design cruise speed. And with those in mind, we created a wing with these properties. To achieve the goal of high endurance, we designed the wing to operate at a high wing loading to reduce power loading. The high lift airfoil MH114 allows us to design around a 65 Newton per meter square wing loading, which brings our power loading down to 5.5 watts per Newton. To further improve performance, the wing is tapered at a 0.46 taper ratio. This maximizes efficiency of our wing. All of these traits, coupled with our propulsion system, estimates endurance at about 63 minutes, which meets our requirement. The large wing area and aspect ratio of the wing, in addition to the components in the previous slide, allowed the wing to have a maximum L on D at 14.99 meters per second, which is our cruise speed. This satisfies goals of efficient cruise, and the stall speed is located at CL max, which is 9.16 meters per second. This stall speed, along with our propulsion solution, allows us to hand launch without crashing to the ground. For the tail, we wanted something that was easy to manufacture, so we chose symmetric airfoil, the NACA 0012, 12% thickness. And using a mix of historic values and X-flyer analysis, we sized the horizontal and vertical stabilizers. We designed the tail to give the aircraft a cruise trim angle of 1.2 degrees at 15 meters per second. And to mount the tail, we used a modular 3D printed part to mount it to the tail boom. This allows us to control the incidence angle of the horizontal stabilizer. Next, we did AVL analysis to determine stability of the aircraft. And with the AVL values we got, it shows that we meet the standard requirements for stability. And the control surfaces we tested in AVL to get these coefficients of moment due to each control surface, which give us enough control authority to maneuver the aircraft. For center of gravity, our calculated goal in static margin was 11 centimeters from the leading edge, which is about 9% mean aerodynamic chord. From our glider, we were able to attain a center of gravity around that same location, which yielded the same static margin. This is an estimated weight and balance CG location of our aircraft based on estimated weights for the wing and fuselage, and then the real weights of the tail and boom from our glider, and then the weights we got from spec sheets for all of our electronics inside the aircraft. And this puts our CG location at exactly what we wanted, which is 9% mean aerodynamic chord. To size our wing spar, we used AVL to get a lift distribution of the wing near stall, this produced about 33 Newton, or about 33 pounds of lift, which is a little over twice our cruise loading. And so with this lift distribution and numerically integrating across the spar, we got estimated wing deflection, and use this along with varying the bending modulus to find a bending modulus that was acceptable for our desired tip deflection. The tail loading was modeled just as a simple point load on a cantilever beam, and we varied the bending modulus to get it below the desired tail deflection. And with this, we sized the wing spar to be a round pull-treated carbon tube with 20 millimeter outer diameter, 18 millimeter inner diameter, and the tail boom is a square carbon tube with 21 millimeter outer diameter and 19 millimeter inner diameter. This is our propulsion setup for our aircraft. We have twin engines mounted on each wing, and as you can see, the load path for these 3D mounted motor mounts is through the skin of the wing, and testing will be done to determine if this is viable or not, with an alternative motor mount in development right now to transfer the motor loads through the spar if this one doesn't work. So for propulsion analysis, we did propulsion analysis through MotoCalc, and we get this thrust required versus motor thrust curve with our greatest excess thrust at around our cruise speed. Max propellant efficiency at cruise is 70%, and we get a static thrust to weight ratio of 0.67%, which gives us the ability for a successful hand launch. And with this motor configuration solution, we get estimated endurance of 63 minutes. So for summary, for aircraft performance, we get trim lowering attack at 1.2 degrees. We get efficient cruise at 15 meters per second with an estimated endurance of 63 minutes, which gives us estimated range of 56.7 kilometers.
Hello, this is Andrew from Georgia Tech, and I'll take us through the rest of the presentation. To help select the components of the payload, an analysis on the software's limits for image detection was performed. This was done by taking an image of people with known heights and calculating the ground sampling distance, or GSD, which is the distance each pixel captures. For the baseline test, the image had an initial GSD of around 0.85 centimeters per pixel. Next, the image resolution was decreased in halves until the software was no longer able to detect a person. The analysis concluded with a maximum GSD of 6.5 centimeters per pixel. Next, that result was tested with a different image. In this image, one of the furthest people was selected to be the focus of the test. The image quality of the original picture was modified so that the person selected matched the limit calculated from the previous slide. Then the image was passed through processing and resulted in the person still being identified. Further tests like this are planned as we get more test data through our contacts. This is our final list for the payload component selection. The processor has an integrated GPU with a capability of up to 8 gigabytes of video RAM, which enables it to be able to process images quickly and accurately. The carrier board selected is compatible with the processor and has the ability to communicate with the chosen peripherals. The gimbal has 3 degrees of freedom and is compatible with the Pixhawk and the camera. And the camera and lens combination were chosen with our GSD calculations and budget in mind, with the varifocal lens giving us flexibility with cruising altitude as we can change the focal length of the camera. The high-powered transmitter is perfect for our application as it allows us to transmit data over long distances with minimal data loss and attain some limited control of the processor. Here we lay out our power at cruise. As seen on the table to the left, the main sources for energy consumption will be the 2 motors with 140 watts and the processor with 15 watts. They'll be powered by 2 separate batteries, with a propulsion battery for the motors and systems battery for the processor. The table on the right gives information on the batteries with the expected time the batteries can power the entire system on the last row. From our calculations, we expect the batteries to be able to power our whole system for an hour. Next is our wiring diagram. The main purpose of this diagram is to highlight which port each component connects to on the larger boards. The diagram is roughly divided into 2 halves with the main payload components to the left and the avionics and propulsion components to the right. Here we have how the components will be laid out in our UAS. From the side view, the components will be placed on a tray that goes inside our fuselage with the electronics velcroed to the top. And the batteries were initially going to be strapped to the bottom of the tray, but we recently increased the battery capacity, which means that the batteries will have their own separate tray below the electronics tray. The electronics tray will have a gap at the front where the gimbal will be slid in and secured. The top view details the relative position of the electronics and the wires connecting them. Most of the components are at the front of the tray to minimize wire length and to maintain the CD imbalance calculated previously. Looking towards testing, we took the risks that we developed in the past from the PDR and used them to develop tests in the future to understand their impact and reduce their likelihood. And this table is an example of the risks that we considered. This leads us to this table with the tests we plan on doing later as our components start coming in. We got together as a team to make a list of tests with risks and key requirements in mind. For risks, as stated before, we want to be able to minimize risks and have a mitigation strategy in place in case it does happen. For key requirements, we want to validate their systems and components are performing per our design. For the budget, we're happy to say that we have managed to decrease our cost by $500 from $5,500 to $5,000. This is mainly from manufacturing getting a more accurate estimates on the materials that we need for producing the UAS. The decreases in payload and avionics came from selecting more suitable alternatives for a few of the components. For schedule, the manufacturing and testing sections were modified to reflect the new timeline we expect to follow as a team, with component production pushed back and more time allocated to testing than in our previous schedule. Other than that, we are still on track with our schedule and have not had any major delays or setbacks. In conclusion, moving forward, we want to conduct more testing and simulation with plans to do wind tunnel testing at Purdue, FAA modeling of our structures, and propulsion endurance and range testing with our components. From the conclusion of testing simulations, we will update our tail and wing mount design as necessary. Along with that, we will also continue to develop alternative motor mount designs in response to constructive feedback that we have received. At this point, I'd like to open it up for any questions you might have for us. Thank you.
This is Todd Harless from Boeing, and I believe I heard one of the questions could be on the heat. And I see a tight compartment that we want to place the electronics in, and maybe I don't have all of the information, and I do apologize, but I didn't see that as a risk, and I wanted to know if there was a way that you guys had already mitigated that, and that's why it was not a risk. And then also, what are the major heat components that you're finding? Is it on that power board itself? Because it wasn't clear to me, and I guess I'm just curious at this stage if that's where it is that the board that will be Velcro to the top up there?
Yes, so here in this slide that we're on, number 36, one of the risks was the computer overheating.
It's the computer, okay.
Yes, so that will be the processor, and right now we've tried to mitigate that with our design of the ventilation slots underneath the fuselage. We're also thinking of putting a heat sink on top of that, and that will be our major source of heat for the fuselage.
So certainly I think it could be, but what about the power electronics that were visible? Have that been studied or declared already through analysis that it's not going to be a concern of heat through the power?
We're under the impression that those are a pretty minimal amount of heat generation compared to the GPU.
Okay. All right, thank you.
Still have a couple more minutes if anybody else has questions for Team 4.
Yeah, it's Philippe at Boeing. Your horizontal tail looks small. I wonder how you sized it. And I seem to remember airfoils with high camber are more difficult to keep stable. And you have pretty much camber, which is good for your mission.
So, in regards to the tail, the vertical and horizontal stabilizers,
we looked at a lot of previous aircraft that were similarly sized to ours to get a historical estimate. After which we used those numbers and then we tested those in AVL to make sure that our stability was within the ranges that we were expecting.
Okay, and the vertical looks really large compared with the horizontal if you look at typical model airplanes.
Right. So our vertical is actually a little bit bigger than we designed it to be in our actual manufacturing. There were some numbers that were moved around during manufacturing, which caused us to have a larger vertical stabilizer. The actual design one, this was about 0.48 meters with vertical. The actual design one is 0.4 meters.
Okay, and this mount you have there, it looks like a lot of drag. Did you do you have plans to streamline things better and get a little more performance?
Yes, absolutely. So this was our first iteration tail mount, which we built just to get an understanding of how well this works, and if this works, we have plans to further downsize it while maintaining the stability of the mount.
Okay, very good.
This is Todd from Boeing again, and I'd actually like to talk about the system concepts, if I may. Some of the terrain, especially out in the very dense areas, could be mountainous, and you could have loss of signal. And I saw that you had a ground station with a backup of a GPS to locate the device, but I was curious, is any of the operations being handled if you were to lose the signal during operation? Essentially, what would happen in the autonomous space here? Would it try to take over and find the signal? Would it try to go back home? Has that been handled?
So in the case of, if we can actually go to the risk assessment slide, well, we've taken into account the chance of losing signal, at which the aircraft will immediately go to a return to landing program.
Okay. So it will try to basically find its way back through some sort of map techniques. Is that what I'm hearing? It will handle it through some sort of concept of trying to get home?
Not necessarily. It's just going to descend and then try to land.
Oh, so it will try on its own to just put itself on the ground?
Right.
I see. Has any thought been given to trying to keep the mission alive and keep it looking for signals, or is that just something that is perhaps a little bit too challenging for the time and schedule?
I don't believe we've spent too much time on that. I believe, Andrew, you might be able to give a better answer on that than I can.
Can you repeat the question again? Sorry.
Sure. If we were to lose signal for this particular mission for this aircraft, it sounds like the aircraft would simply try to place it down safely and locate to its operators where it's at. And I was just curious, in the system operations, the system engineering side, have we put any thought on trying to keep the mission alive instead of just trying to place it on the ground? Is there alternate solutions of trying to find the signal again or keep the mission alive to then come back and reconnect with the operator?
So our plan was to make a flight plan and go through a path to try and find people with the camera and image processing. We would assume that it would do this autonomously and then come back to the ground station once it completed the flight path. If there was something going wrong with the UAS, such as like motor failure, we would try and let it try and land somewhere on the ground safely. But we haven't thought of a signal loss, something like that. The transmitter that we selected is really high powered and could transmit 11 kilometers pretty easily. So I don't think, I'd say that it'd be a low risk on losing the UAS.
I just want to make sure that, in mountainous terrain, if you were to launch a vehicle, because people can't get to that area and they're trying to observe it, if there are situations handled or not. And it's just something I bring up that I think a stakeholder may wish to also ask about, but it's nothing that I'm not pushing the team here. I was just curious if that was something thought of, and I I do understand that, there are ranges that seem like it would be safe and such, and perhaps this is where I think somebody had mentioned the stakeholder. It's just options that, scenarios up at the system engineering level that could be thought of is all. I'd like to just offer as guidance because these are things certainly in the autonomous space that I think are challenges.
Yes, certainly. I thank you for bringing that up, and we'll consider that from now on, and we'll try and.
That's absolutely a good concern to bring up. One thing that has kind of influenced the fact of how much time we spent on it is our optimal design space and kind of like the operation range that we're using the UAV for isn't really around mountainous ranges. So we hadn't had to take into consideration signal blocking by that effect. Since we're more of a search and rescue of like post-hurricane scenarios, mostly flatlands is what we've kind of identified as our work area.
Sure, and I think you guys have done a really great job. I just think that if the scenarios could be thought up more up there, I think it helps with any sort of gotchas or mistakes later on in the production cycle that could be really much more expensive and harder to achieve solutions if you're, say, for instance, already baked in on a certain solution and you didn't think of those concepts. I just want to make sure that the team understands that there is value to truly try to understand, what could happen though if you were in a forested area and you have a ground station, you could still lose signal certainly. And there can be effects that you may not be thinking of that you'd think are ideal. And I would just encourage the team in that space for any future development to think through all of those first to make sure, because then your design can handle those and not have to handle change later on.
Right, absolutely. Thank you for bringing that up. We'll definitely spend a little bit of time on trying to solve that.
Sure, certainly. Thanks.
With that, we're at 1:30 Eastern. Once again, if any Boeing or external viewers would like to provide feedback, you should have access to the link to do so, and that'll get fed back to the teams early next week, hopefully. So, with that, I guess we'll call the CDR complete. And I guess teams, you can just write until next week then. All right. Keep in mind that rolling feedback from today's presentations into the final report is highly encouraged. So do that. Everybody have a nice day. Have a pleasant tomorrow.